Welcome to the deep dive. Our mission today is, well, we're strapping ourselves into what might be the fastest machine in materials science right now. We're talking about the autonomous AI-driven factory that's really starting to revolutionize how we discover and even manufacture the building blocks of the future.
Yeah, and it's more than just putting a robot arm in a lab, right? We're
Hmm.
moving beyond simple automation. This deep dive is about understanding how generative AI, specifically these large-scale foundation models, mesh with physical robotics to create systems that are genuinely autonomous, self-improving even.
Self-improving, okay.
We're watching this huge shift where tasks that used to take researchers years, painstaking, expensive trial and error, are being compressed into workflows that run in days. It feels like this is the moment where computational power really finally connects properly with experimental reality in the lab.
Because that's always been the hang-up, hasn't it? The bottleneck in discovering new materials wasn't necessarily a lack of ideas. A chemist could dream up 1,000 new compounds, theoretically. But the sheer time and cost, the unreliability sometimes of actually mixing, heating, analyzing even one of those in the lab, well, most ideas just stayed ideas stuck on a computer somewhere.
Exactly that gap, that chasm between a theoretical prediction and actually holding the thing in your hand, experimentally realized. That's been the defining challenge, maybe the frustration in material science for decades. So what we're digging into are two major breakthroughs that work together to, well, basically smash that bottleneck.
Yeah.
You can think of the whole setup as this tightly integrated materials discovery flywheel.
A flywheel. Okay, I like that. So let's break it down. The first pillar is, what? The computational brain. Google DeepMind's GNoME.
Right, GNoME, that stands for Graph Networks for Materials Exploration. Think of it as the generative AI foundation model that's designed specifically to just massively scale up our theoretical knowledge base, the list of what stable materials could exist.
So GNoME narrates the blueprints, the possibilities.
Exactly, a huge, high-quality list of theoretical blueprints. But, a blueprint doesn't build itself. Which brings us to the second pillar, the A-Lab, the autonomous laboratory.
The builder.
The builder. The A-Lab takes those theoretical targets that GNoME spits out and uses this combination of self-driving robotics, machine learning for analysis, and active learning algorithms to actually try and physically synthesize them, make them real.
So it closes the loop. Computation suggests, experiment tries, and then the results from the experiment feed back to make the computation smarter next time.
That's the core idea. Understanding how these two pillars talk to each other, how they scale together, how they learn from success and failure. That's what we're going to unpack in this deep dive.
Okay, let's start with GNoME then, because before you can build anything autonomously, you need that list, right? A really good validated list of what's even theoretically possible. You said GNoME solved the scaling problem here. What kind of scale are we really talking about? Just how big a jump was this?
Oh, it's genuinely monumental. Think about the entire history of computational materials science put together. All the big databases, the Materials Project, OQMD, the ICSD. If you take all the known computationally stable crystalline materials from basically decades of research,
Okay.
hundreds of millions of CPU hours, thousands of researchers, you ended up with about 48,000 unique, stable compounds based on recalculated, consistent metrics.
48,000, that's the baseline accumulated over like half a century of effort.
That's the baseline. Now, GNoME, using these generative AI principles, these graph networks, and just massive compute power, discovered 2.2 million structures that were predicted to be stable relative to previous known materials. But the really crucial number is how many of those are truly thermodynamically stable, sitting right on what we call the convex hull.
Right, the absolute lowest energy state.
Yes. GNoME yielded 381,000 new entries, sitting right on that stability boundary. These are fundamentally new, stable materials we didn't know about before. So we went from roughly 48,000 to adding another 381,000. It's almost a tenfold expansion,
Yeah.
an order of magnitude jump in our basic knowledge of stable inorganic crystals from one project.
Wow. Okay, that's nearly 10x increase. That's staggering. It really shifts the paradigm, doesn't it? From scientists maybe having a hunch and testing a few things to this massive AI-driven exploration of the possibilities. But hang on, 381,000 new stable compounds predicted by an AI, How much can we, trust that number? Are they real?
That's the absolutely essential question, and skepticism is healthy here. The validation is pretty strong, actually. Even before the A Lab started trying to make them, other research groups, totally independently, had already experimentally synthesized and confirmed 736 of the specific structures GNoME predicted.
Ah, okay. So independent experimental verification was already happening. That builds confidence.
Exactly. It suggests the underlying model isn't just making things up, it's identifying genuinely plausible, synthesizable targets.
Right. So let's get into the mechanics a bit. How does GNoME actually work? What's under the hood of this generative AI foundation model that lets it process materials and scale like this?
The heart of GNoME is a type of neural network called a graph neural network, or GNN. These are particularly well suited for crystals. Unlike, say, a standard network looking at a flat sequence of data, GNNs inherently understand connectivity and relationships, perfect for atoms in a lattice.
Okay, so walk us through that. How does a crystal structure, atoms and bonds, turn into something this GNN can process?
You basically represent the crystal structure as a network graph. It's quite intuitive, actually. Each atom in the crystal becomes a node in this graph.
Right.
And the information on that node is essentially its chemical identity, like, is it oxygen,
Uh,
silicon, lithium? This is usually done with something called a one-hot embedding, which is like a unique digital fingerprint for each element.
okay, so nodes or atoms. What about the connections, the bonds?
The bonds, or even just the spatial proximity between atoms, become the edges connecting these nodes in the graph. So the GNN gets this network representing the crystal's structure and chemistry.
And it processes this graph using message passing, you mentioned. What does that mean? Sounds like atoms chatting with each other.
That's actually a really good way to think about it. In message passing, each atom node sends information a message about its state to its direct neighbors in the graph. Then, each node gathers all the messages it received from its neighbors, combines that incoming information with its own current state, maybe runs it through a small neural network, and then updates its own state, or passes a refined message along in the next step or layer.
So it's iterative. The information kind of ripples through the structure.
Exactly. It allows the GNN to learn about the local chemical environment around each atom first, and then, as messages propagate further, it builds up an understanding of the larger global structure and its properties.
And the ultimate goal of all this message passing and aggregation.
The main goal for GNoME was to predict the total energy of that crystal structure very, very accurately, because energy tells you about stability. These aggregate projections, the math that combines the messages, are typically handled by things called multilayer perceptrons, or MLPs, which are sort of the standard workhorses within neural networks.
Okay, so it predicts the energy. How accurate was it initially?
The initial GNN models they developed achieved what's called a mean absolute error, or MAE, of about 21 millielectron volts per atom. 21 MeV per atom.
21 MeV per atom. Now, put that in context. Is that good? Bad? Why did they need to push it lower?
It's okay, but not quite good enough for reliable discovery at the cutting edge. In materials science, the energy differences that determine whether a material is truly stable on the convex hull versus just slightly unstable, maybe decomposing into other phases. That difference is often really small. We're talking maybe 10, 20, 30 MeV per atom.
Ah, I see. So if your average prediction error, your MAE, is 21 MeV.
You're right in that zone of uncertainty. You're going to make a lot of mistakes right at that critical stability boundary. You'll predict something is stable when it isn't, or vice versa. It makes efficient discovery really hard.
You're basically flipping a coin on stability for the most interesting cases near the edge.
Pretty much.
Yeah.
But through massive scaling, developing clever techniques like SAPS, symmetry-aware partial substitutions, to generate millions of diverse candidate structures efficiently and, importantly, through this active learning loop, they managed to drive that error down dramatically.
Right.
They got it down to just 11 MeV per atom.
From 21 down to 11 MeV per atom, that's almost halving the error.
Yes. And that reduction, that extra 10 MeV per atom of accuracy, is absolutely critical. It's the difference between constantly chasing ghosts and having genuinely high predictive power right where you need it at that thermodynamic stability edge.
Okay, and you mentioned active learning. That's the data flywheel concept. Can you break down how that loop works? How does feeding data back make the model that much better?
It's a really elegant, iterative, self-improving cycle. Step 1. You train your GNN on the best available existing data, say structures and energies, from the materials project database.
Okay, train on known stuff.
Step 2. You use that trained GNN to rapidly screen millions, maybe even billions, of new candidate structures. These are structures generated by substituting atoms, distorting lattices, combining known structures. The GNN prediction is super fast, computationally cheap.
But it's like a quick, rough filter.
Exactly. Based on the GNN's energy prediction, the algorithm filters this massive pool down to only the most promising candidates, the ones the GNN thinks are very likely to be stable, close to that convex hull.
So it focuses the expensive calculations, because
Yeah.
the next step is the slow one, right?
Right. Step 3. You take only those promising candidates, maybe just a few percent of the initial pool, and you perform high-fidelity but computationally very expensive density functional theory, DFT, calculations on them. DFT tries to solve the fundamental quantum mechanics, the Schrödinger equation, for the electrons in the material. It's accurate, but it takes a lot of computing power and time. That's the traditional bottleneck.
So GNoME doesn't replace DFT, it just makes sure you only spend that expensive DFT time on structures that are highly likely to be winners.
Precisely. It acts as an incredibly efficient focusing mechanism. And then, step 4, the crucial closing of the loop.
Mm.
Once the DFT calculation finishes and gives you the accurate, true energy for that candidate structure,
You feed it back?
you feed that structure and its verified DFT energy straight back into the training data set for the GNN. And then you retrain or update the GNN. Now it's learned from that new, high-quality data point.
So the next time it sees a similar structure, its prediction will be even better.
Exactly. That's the flywheel. Each cycle, predict, filter, calculate, retrain, makes the GNN smarter, more accurate, and better at identifying stable materials. That's how they systematically drove the MEE down from 21 to 11 MeV.
Now, this iterative improvement, this learning from data,
Yeah.
it sounds conceptually a lot like how large language models get better by reading more text. You mentioned GNoME is a foundation model. Is there a deeper, maybe mathematical connection here?
Yes, there is. And this is, for me, one of the most profound findings of the GNoME work. They found that the performance of the GNoME model, specifically how much the error or test loss decreases, improves as a power law with the amount of training data, the number of DFT calculations fed back into it.
A power law, wait a minute, that's the same mathematical relationship, the same scaling law that governs how large language models and computer vision models improve with more data and larger size.
Exactly the same. This is huge. It strongly suggests that GNoME isn't just a specialized tool, it's behaving like a true foundation model, but for materials discovery. This power law scaling means improvement is predictable. If you double the data, you get a predictable reduction in error. It implies there's still room to grow, that we haven't hit a fundamental limit yet, as long as we can keep generating that high-quality DFT data.
And that predictable scaling, that foundation model behavior, that's what unlocks what they called emergent generalization. The model starts getting good at things it wasn't explicitly trained on.
Absolutely. That's a hallmark of foundation models. Because GNoME was trained on such a massive and diverse data set through the scaling process, it started showing surprising accuracy for types of materials that were way outside its initial training focus. For instance, predicting the stability of complex compounds with 5 or more different elements.
Which is a nightmare combinatorially, right? The number of possibilities just explodes.
Explodes. Human intuition really struggles there, and earlier, smaller models just couldn't handle it reliably. But the scaled-up GNoME, thanks to this emergent generalization driven by the power law, could navigate that incredibly complex chemical space and make accurate predictions. It learned the underlying rules of chemical stability more deeply.
Okay, so GNoME delivers this enormous validated list, 381,000 new stable compounds. That's amazing fundamental knowledge. But we need materials that do things, right? How does having this vastly expanded list help find materials for specific applications?
Well, the sheer breadth of the data set makes targeted searches incredibly powerful. You can now screen this massive list for specific properties relevant to applications. Take layered materials, things like graphene, or materials used in batteries and electronics. Before GNoME, the known database of stable layered materials was around 1,000 compounds.
Okay.
GNoME expanded that list to 52,000 potential stable layered materials. That's a 50-fold increase in the search space just for that one class of materials.
50 times more options for engineers to explore for the next generation of electronics or batteries.
Exactly. And speaking of batteries, another example. Solid-state batteries need materials that conduct lithium ions really well. GNoME was screened for promising Li-ion conductors. It found 528 candidates that look really good based on structural motifs known to facilitate ion movement.
And how does that compare to previous searches?
A prior, highly cited study, specifically looking for these conductors, found about 2 dozen. So GNoME provided a 25-fold increase in promising candidates compared to that dedicated, focused study. The lesson is clear. Building that huge foundational data set with AI first accelerates discovery across all downstream applications that rely on it.
Right, a rising tide lifts all boats. So that covers the computational powerhouse, GNoME, scaled, accurate, predictable. But like you said, a blueprint is just a blueprint. Now we have to get our hands dirty, metaphorically speaking, in the lab. This is where the A lab comes in, bridging that gap from simulation to synthesis.
Yes, and the A lab is where things get really fascinating. Partly because it's tackling the messy reality of chemistry. Its whole purpose is to be more than just automated equipment. It's designed to be an autonomous experimental agent.
Okay, you drew a distinction earlier between automation and autonomy. Can you elaborate on that? Why is autonomy the goal here?
Think of automation as a robot, following a fixed recipe, maybe stopping if something goes obviously wrong, like a spill. Autonomy is different. An autonomous system, like the A-Lab aims to be, can interpret complex, often ambiguous experimental data, like the pattern from an X-ray diffraction experiment, and then make independent decisions based on that data. It can decide, okay, that didn't work, let's try changing the temperature, or this intermediate phase forms, so maybe I need different precursors. It learns and adapts the plan.
So it's like having a tireless, data-driven lab scientist running the experiments 24/7, one that doesn't get tired or have preconceived notions, maybe.
That's a good way to put it. The A-Lab integrates multiple streams of intelligence. The target list from GNoME, existing materials databases, synthesis rules of thumb extracted by machine learning from thousands of scientific papers, ML models to interpret the experimental results in real time, and active learning algorithms to decide the next best experiment.
And it's focused specifically on making solid inorganic powders, you said. Why is that significant? Aren't powders common?
They are common, but they're notoriously tricky to handle robotically, especially compared to liquids, which is what a lot of automated chemistry and pharma focuses on. Powders clump, they have different densities, they don't flow predictably, the reactivity depends on particle size.
Ah, okay. I can see how that would be a challenge for a robot trying to measure out precise amounts and mix them perfectly every time.
Exactly. You need specialized handling, things like high-energy ball milling to grind precursors together and ensure they react well. The A-Lab had to be engineered from the ground up to manage these solid handling tasks reliably, dispensing tiny amounts, mixing them intimately, transferring them without losing material. It's a much harder robotics problem than just pipetting liquids.
Okay, so this sophisticated powder-handling autonomous lab, what was its first big test? What did they ask it to do?
Its mission was ambitious. Synthesize 58 specific inorganic powder materials predicted to be stable by the GNoME project and related computational work. And here's the kicker. For 52 of those 58 targets, there were no known recipes in the scientific literature. They were completely new synthetic challenges.
Wow, so it wasn't just making known stuff faster, it was venturing into totally uncharted territory based purely on the AI's prediction and its own learned synthesis strategies. How did it do?
Over 17 days of continuous closed-loop operation, meaning the system ran itself, making decisions, running experiments, analyzing results, the A-Lab successfully synthesized 41 of the 58 target materials.
41 out of 58. That's a 71% success rate.
A 71% success rate on novel materials, most with no prior synthesis roadmap. That is a huge validation. It shows that the whole pipeline, from GNoME's theoretical prediction to the A-Lab's autonomous synthesis and adaptation, actually works remarkably well. The AI's predictions are largely pointing towards things that can, in fact, be made.
And this wasn't just one machine, right? You mentioned integrated stations. Can you give us a quick tour of how the A-Lab physically operates?
Yeah, it's basically a mini factory with robotic arms moving samples between three main stations. First is sample preparation. Here, the robot arms have to accurately weigh out and dispense the solid precursor powders, maybe oxides, carbonates, phosphates. Then they need to be mixed really well. Often this involves adding ethanol and some hard zirconia grinding balls into a vial with the powders and putting it in a special high-speed centrifuge, a dual asymmetric centrifuge, that mixes everything into a homogeneous slurry. Then that slurry is dried in a little ceramic dish, a crucible.
Okay, precursors mixed and ready. Then it needs heat, right? Solid-state reactions usually need high temperatures.
That's the heating station. Another robotic arm takes the crucible with a dried precursor mix and places it inside one of several box furnaces. The heating isn't just turn it on high, it follows a precise temperature profile programmed by the control system. Typically, it involved a slow ramp, maybe 2 degrees Celsius per minute, up to 300 degrees C.
Why the slow initial ramp?
That's critical if you have precursors that might decompose or evaporate easily, like ammonium phosphates. The slow ramp gives them time to react and incorporate into the solid structure before they just boil away. After that initial slow ramp, it would ramp faster, say 15 degrees C per minute, up to the main target temperature, maybe 800, 900, 1,000 degrees C, and hold it there for several hours, typically 4 hours, to let the reaction complete.
Okay, cooked for hours. Then what? How does it know if it made the right thing?
That's the final station, characterization. Once the furnace cools down, the robot takes the crucible out. The resulting chunk, or powder, needs to be ground up very finely and uniformly. This is really important for getting good data. Then the powder is put into a sample holder for X-ray diffraction, XRD analysis.
XRD. That's the standard technique for figuring out the crystal structure of a solid, right? It gives you a fingerprint pattern.
Exactly. The XRD machine shoots X-rays at the sample, and the way they scatter off the crystal lattice creates a unique diffraction pattern. That pattern is the raw data feedback. It tells the system what crystalline phases are present in the sample and in what amounts. This is the signal that closes the loop and tells the AI whether the synthesis was successful or not.
Now, interpreting that XRD pattern and deciding what to do next, that sounds like where the real AI and ML comes into play within the A lab itself. How does it generate the initial recipe for a material nobody's made before?
That's a great question. It doesn't just guess randomly. The initial recipes are proposed by a natural language processing NLP model. This model was trained by reading and processing a huge amount of chemistry literature. They text-mined 33,343 solid-state synthesis procedures from over 24,000 published papers.
Wow. So it learned how human chemists describe making materials.
Essentially, yes. It learned the relationships between target materials, precursor chemicals, and synthesis conditions like temperature. So for a new GNoME target, the model looks for known materials that are chemically similar, maybe containing the same elements or having similar structural features. It then used that analogy to propose a starting set of precursors and a promising reaction temperature, mimicking how an experienced human chemist might make an educated guess.
Okay, so it gets a starting recipe from the literature AI, then it runs the experiment, gets the XRD pattern. How does it analyze that pattern to figure out, did I make the target? Especially if the target is novel.
This involves a couple of layers of machine learning for phase identification. First, there are ML models, specifically. They used convolutional neural networks, CNNs, the same type of AI often used for image recognition, to do a quick analysis of the raw XRD pattern. Their job is to identify the crystalline phases present and estimate their approximate amounts or weight fractions.
But wait, if 52 of the targets were brand new, how could a CNN be trained to recognize their XRD patterns? There wouldn't be any real experimental data to train on.
That's the clever part, and where the synergy with GNoME is critical. They train the CNNs not on real experimental patterns, but on simulated XRD patterns generated computationally from the theoretical crystal structures predicted by GNoME.
So you use the theoretical prediction to create simulated fingerprints and then train the AI to look for those fingerprints in the real experimental data coming off the XRD machine.
Exactly. It allows the A lab to recognize success, even for material that has never existed before. And then, to get a more precise quantitative confirmation, the system performs an automated Rietveld refinement. This is a standard, more complex analysis technique that finely tunes the crystal structure parameters, like the exact dimensions of the repeating unit cell, atom positions, to get the best possible match between a calculated pattern and the measured experimental pattern.
And that's automated too. Rietveld refinement usually takes a human expert quite a bit of time.
Here, it's controlled by a reinforcement learning RL agent. This RL agent has two deep neural networks, an actor that proposes changes to the refinement parameters, and a critic that evaluates how good the match is. It iteratively adjusts things to find the best fit, confirming the phases and their precise amounts, all without human intervention. This refined result is the high-quality feedback for the next step.
Okay, so that confirms the successes, the 71%. But the real intelligence often lies in learning from failure, right? You said the initial recipes, the ones inspired by the literature AI, actually failed quite often.
They did. 63% of the time, in fact. 225 out of the 355 initial recipes tried did not produce the desired target material as the main product. This is where the autonomy really kicks in, driven by the need to optimize.
So before we get to the optimization algorithm, let's touch on the underlying physics. Thermodynamics tells us these GNoME targets should be stable, right? They're on or near the convex hull.
That's the prediction, yes. The convex hull, maybe think of it like this. Imagine a landscape where elevation represents energy for all possible chemical combinations of certain elements. The convex hull is like stretching a sheet over the deepest points in all the valleys. Anything lying on that sheet is thermodynamically stable. Anything floating above it wants to decompose down onto the sheet.
It's the ground state, the most stable configuration.
That's 0 Kelvin, yes. GNoME specifically targeted materials predicted to be right on that hull, or only a tiny bit above it, maybe less than 10 MeV per atom.
And the metric used to quantify that stability is the decomposition energy.
Correct. A negative decomposition energy relative to known stable phases means the material is predicted to be stable. A positive one means it's predicted to decompose. But here's one of the most interesting findings from the A-Lab experiments. They found no clear correlation between how stable a material was predicted to be, its decomposition energy, and whether the A-Lab could successfully synthesize it.
Wait, really? So just because the theory says it's super stable doesn't mean it's easy to make?
Exactly. It highlights a crucial point, often overlooked in purely computational searches. Kinetics matter enormously. Just because a final state is low energy doesn't mean the reaction path to get there is easy or fast. You can get stuck in intermediate states, reactions can be incredibly slow, other competing reactions might happen faster.
It's like knowing the bottom of the valley exists, but the path down is blocked by a huge mountain range you have to climb first, or you get stuck in a smaller ditch halfway down.
That's a perfect analogy. The real world of synthesis is governed by these kinetic barriers and reaction pathways, not just the final thermodynamic endpoint. And since those initial recipes failed 63% of the time, the A-Lab clearly needed a smarter way to navigate this kinetic landscape.
Enter AROS-3. This is the active learning algorithm for optimizing recipes. How does it work? What does it do when a recipe fails?
Right. AROS-3 autonomous reaction route optimization with solid-state synthesis is the algorithm that proposes follow-up experiments when the initial guess fails. It operates based on two core hypotheses, derived from general solid-state chemistry knowledge, but applied systematically by the AI.
Okay, what are these two guiding hypotheses?
Hypothesis 1. Solid-state reactions, even complex ones, tend to proceed through a series of simpler, pairwise reaction steps, meaning usually only two distinct solid phases are reacting with each other at the interface at any given moment. This simplifies how the AI thinks about the reaction pathways.
Okay, pairwise reactions. And the second hypothesis?
Hypothesis 2, and this one is really key for optimization. Intermediate phases that form during the reaction but leave only a small thermodynamic driving force to reach the final target product should be actively avoided.
Okay, unpack that. A small driving force, meaning the intermediate is almost as stable energetically as the final product you want.
Exactly. If an intermediate phase forms, and the energy difference between that intermediate and your desired final material is very small, say, only 5 or 10 MeV per atom, the reaction essentially stalls. There's very little push to get over the final activation barrier and complete the transformation.
It's like trying to roll a ball down a very, very gentle slope. It might just stop due to friction.
Precisely. These small driving forces lead to incomplete reactions, needing excessively high temperatures or extremely long times, which might cause other unwanted side reactions or decomposition. So AROS-3 learns to identify these thermodynamic traps.
So how does it use these hypotheses? It sees a failure, analyzes the intermediate phases formed using the XRD and ML analysis.
Yeah.
Then what?
It uses the analysis of what did form to infer which pairwise reactions likely occurred. It continuously builds a database of these observed pairwise reactions from all the experiments it runs successful or not. In just those 17 days, it logged 88 distinct pairwise reactions it had witnessed.
So it's learning the reaction network on the fly.
Yes, and by knowing which pairs react to form which products, and knowing the thermodynamics, it can predict if a different set of starting precursors might lead down a path that avoids those problematic intermediates with small driving forces. It actively seeks out reaction routes that have intermediates with a large driving force towards the target.
It's trying to find the reaction pathway that has the steepest downhill slope at the end.
That's the idea. And because it builds this database of observed reactions, it gets more efficient. If it sees two different proposed recipes that its internal model predicts will lead to the same problematic intermediate, it can avoid running the second redundant experiment.
How much did that help? Does it prune the search space significantly?
They estimate that this ability to infer products and avoid redundant tests based on learned pairwise reactions can reduce the experimental search space by up to 80% in some cases. It stops the system from blindly trying variations that are doomed to fail for the same underlying kinetic reason.
Can you give that specific example they mentioned, the synthesis of Cafe2P209?
Yes, that's a great illustration. The initial recipe temp for Ca2p209 failed. Analysis showed it formed intermediate phases, but the calculated thermodynamic driving force from those intermediates to the final Ca2p209 target was tiny, only 8 MeV per atom. Just like the hypothesis predicted, the reaction stalled. Yield was near zero.
Okay, 8 MeV. Almost flat energetically.
So Arrows 3 kicked in. Based on its learned reaction data and thermodynamic calculations, it proposed a different set of precursors. This new route was predicted to form different intermediates, ones that had a much, much larger driving force, 77 MeV per atom, towards the final target.
From 8 MeV to 77 MeV, that's a huge difference in the thermodynamic push.
A huge difference. And when the A lab ran this Arrows 3 suggested recipe, the synthesis was successful, achieving roughly a 70% yield of the target Ca2p209. It's a direct experimental validation. The AI identified the kinetic trap, small driving force, and autonomously found a pathway around it, dramatically improving the outcome.
That's genuinely impressive. The AI isn't just following instructions, it's analyzing failures, applying chemical principles, and redesigning the experiment for better kinetics. Okay, let's loop back to GNoME for a second, because the sheer scale of that data set, the 2.2 million structures, enabled something else quite profound. The training of next-generation machine-learned interatomic potentials, MLIPs.
Yes, this is another major downstream benefit. Crucially, the GNoME dataset didn't just contain the final, relaxed, lowest energy structures. It also contained the trajectories, the step-by-step atomic movements recorded during the DFT structural relaxation calculations.
So not just the final snapshot, but the movie of how the atoms move to get there.
Exactly. Having that dynamic data, showing how forces between atoms change as the structure distorts, was incredibly valuable. It allowed them to train highly accurate general-purpose MLIPs, like one called GNoME, on an unprecedented scale and diversity of chemical environments.
And why are these MLIPs such a big deal? What do they let you do?
MLIPs aim to capture the complex relationship between the arrangement of atoms and the potential energy of the system, just like DFT does. But they are orders of magnitude faster computationally. This speed unlocks the ability to run large-scale, long-time molecular dynamics, MD simulations.
MD simulations. That's where you simulate the actual movement of atoms over time, like watching a chemical reaction happen or ions moving through a battery material.
Precisely. These are essential for understanding and predicting dynamic properties like ionic conductivity, diffusion, phase transitions, reaction mechanisms, things that are often too slow or too large scale to simulate directly with expensive DFT. MLIPs bridge that gap, offering near DFT accuracy at a fraction of the cost.
Okay, so faster simulations. But the really striking claim was about zero-shot generalization. What does that mean in this context?
Zero-shot generalization here means that these MLIPs, trained only on the structural relaxation data from GNoME, essentially data near 0 Kelvin temperature, demonstrated remarkable accuracy when used to predict dynamic properties like ionic conductivity in MD simulations run at much higher temperatures, like 1,000 Kelvin, and for chemical compositions they had literally never seen during training.
Whoa. So the potential learned the fundamental physics of how atoms interact deeply enough from the GNoME data that it could accurately predict how different atoms would behave and move in completely new materials and under very different conditions, high temperature, than it was trained on.
That's the essence of it. It suggests the potential learned something fundamental about the interatomic forces, not just memorizing the training structures. The richness and diversity of the GNoME relaxation trajectories were key. This robustness is a huge step.
And this makes them more useful in practice.
Immensely. They showed that these GNoME pre-trained potentials exhibit systematic improvements in transferability. Even when you take one of these general potentials and fine-tune it on a small, specific data set for a particular task, like predicting conductivity in a specific battery chemistry, it often performs as well as, or even better than, models that were trained from scratch only on hundreds of data points just for that specific material family.
So pre-training on the massive, diverse GNoME data set gives the potential a huge head start, a better foundational understanding.
Exactly. It confirms that GNoME isn't just a static list of stable compounds. The underlying data it generated is rich enough to serve as a true foundation model for building powerful, generalizable tools like these MLIPs, accelerating research in dynamics and kinetics too.
Okay, foundation models, autonomous synthesis. It sounds incredibly powerful. But let's bring it back to the A Lab's initial run. We celebrated the 71% success rate, but what about the other 29%? The 17 targets the A Lab failed to synthesize. What can we learn from the failures?
The failures are, in many ways, just as important as the successes. They provide critical feedback, highlighting the boundaries of our current understanding and capabilities, both experimental and computational. They broke down into roughly 4 categories.
All right. What was the most common reason for failure in the A lab?
The biggest category, accounting for 11 out of the 17 failures, was attributed to slow reaction kinetics. This often goes back to what AROS 3 tries to fix: low thermodynamic driving forces. Or maybe the initial mixing wasn't good enough, or the temperature just wasn't high enough for long enough.
So, problems that are potentially solvable, maybe with more time, higher heat, or better mixing.
Often, yes. The researchers noted that many of these might be fixable with techniques slightly outside the current autonomous loop, like intermediate grinding steps to refresh particle surfaces, or simply running the reaction hotter or longer. If you optimistically assume these 11 are kinetically limited but ultimately solvable, the potential true positive rate of GNoME's predictions might be closer to 74%.
Okay, slow kinetics. What else went wrong?
Another issue was precursor volatility. Some starting chemicals can just evaporate before they have a chance to react properly, especially at high temperatures. They saw this with a target containing ammonium phosphate. The phosphate component likely vaporized above 450 degrees C, changing the overall chemical ratio, the stoichiometry, and preventing the target phase from forming.
Ah, so the ingredients disappear mid-recipe. How does the AI learn from that?
The feedback is direct. The system learns that for certain volatile precursors, the reaction pathway needs to be designed differently. Maybe use a different precursor, or find conditions where the volatile component reacts quickly at a lower temperature to get locked into a stable intermediate before it can evaporate.
Makes sense. Any other experimental failure modes?
One target just refused to crystallize properly. It formed an amorphous material instead, basically, the disordered glassy state, rather than the desired ordered crystal. The target was MoPO35. Computational analysis confirmed that for this composition, the amorphous state was also quite low in energy, meaning there wasn't a strong energetic preference for it to crystallize.
So the material preferred being messy over being organized. Another kinetic trap, in a way.
Exactly. The system needs to learn to recognize compositions that are prone to forming these stable or metastable amorphous phases.
Okay, so kinetics, volatility, amorphization, those seem like experimental challenges. But you mentioned some failures pointed back at the computational predictions themselves, where GNoME or the underlying DFT might have been wrong.
Yes, and this is where the A-Lab truly acts as an experimental oracle, directly validating or refuting the theoretical predictions. At least 3 of the 17 failures were ultimately attributed to inaccuracies in the initial DFT calculations that GNoME relied upon.
How did they figure that out?
Take the target Le5M5016. Every attempt the A-Lab made produced a known, simpler compound, LAMINO3. But when they checked the original DFT calculations used by GNoME, those calculations actually predicted that the known LAMINO3 phase should be highly unstable.
Whoops. If the calculation gets a known stable material wrong, you can't really trust its prediction for the new related material.
Precisely. It tells you that the specific flavor of DFT used, or the approximations made within it, aren't capturing the physics correctly for that particular chemical system, perhaps due to complex electronic effects like John-Teller distortions common in manganese oxides, or maybe issues with the pseudopotentials used to simplify the calculation, as suspected in another failure involving ytterbium molybdate, YBMO4.
So the experiment directly tells the theorists, your model has a blind spot right here.
Exactly, and that feedback is gold. It allows the computational chemists to go back, refine their methods, maybe use more accurate and expensive levels of theory for those specific tricky chemistries, and improve the underlying DFT models.
And if they fix those DFT errors, the flawed predictions would disappear from future GNoME runs.
Correct. Those targets would likely be recalculated as unstable and wouldn't be pursued by the A-Lab. They estimated that correcting just these few identified computational inaccuracies would bump the theoretical prediction success rate from the initial 71% up toward 78%. These discrepancies are not just failures. They are crucial signals, pinpointing exactly where our fundamental theories or their computational implementations need improvement.
This whole cycle is really something. GNoME scales up theory, A-Lab tests it autonomously, AROS 3 optimizes the failures, and the remaining failures feedback to improve the theory itself.
It's a powerful demonstration. Over those 17 days, the A-Lab wasn't just making materials. It was realizing fundamentally new crystalline solids at an average rate of more than 2 new compounds per day.
Huh.
With minimal human oversight. That speed is just unthinkable compared to traditional solid-state synthesis workflows.
and all built on the foundation of GNoME having already expanded the theoretical map by nearly tenfold. It really feels like the integration of the AI prediction, the ML analysis, the robotics, the active learning. It's not just making things faster, it's changing the very nature of how scientific discovery can be done, moving from slow, intuition-heavy searches to this rapid, autonomous, data-driven exploration.
The autonomous research agent, at least in this domain, is clearly becoming a reality. It can manage so much of the discovery pipeline now.
But like you said, the journey isn't over. Those failures, those discrepancies, they show there's still more to learn, especially about kinetics and complex reactions.
Absolutely. Refining our understanding of synthesis pathways, especially for materials that aren't perfectly thermodynamically stable, is the next big challenge.
Which brings me to a final thought. We've seen how this AI-driven system dramatically accelerates the discovery and synthesis of stable materials, the ones on or very near the convex hull. That's the essential foundation. But many of the most exciting materials for future technologies, think advanced catalysts, next-gen computing, maybe even better battery electrodes, often rely on materials that are metastable. They exist slightly above the hull in those little ditches, not at the absolute bottom of the valley. They're useful because they're not perfectly stable, but they're hard to make and keep.
That's a critical point. Metastatability is key to function in many advanced materials.
So the next frontier seems clear, doesn't it? Can we train these autonomous systems, the GNoMEs and A-labs of the future, to go beyond just finding stable compounds? Can we teach them to master the delicate art of synthesizing and controlling these complex, dynamic, metastable materials? To optimize not just for did I make the phase, but for microstructure, defect density, things that directly impact performance.
That's exactly where this needs to go. Moving beyond just synthesizability towards targeted function, controlling the structure at multiple length scales.
If generative AI like GNoME can write the initial recipes, and optimization AIs like Arrow's S3 can figure out the kinetics, could these systems eventually learn to cook these complex metastable materials with a precision and speed that surpasses even the most experienced human chemist? Can AI become not just a discoverer, but a master craftsman of the materials that will define our future?
That's the provocative question, isn't it? And based on the rapid progress we're seeing, the answer might come sooner than we think as these systems continue to learn, especially from their failures.
Definitely something to keep an eye on. Thank you for joining us on the Deep Dive.